Tonight, we are going to drift gently through a simple question that reaches across the entire universe. How does gravity work in space? It is a question that can feel very large at first, because space is so wide, so quiet, and so full of distant worlds. But we will take it slowly. We will move step by step, with no hurry at all. We will let each idea settle before moving to the next one. Gravity is one of the most familiar forces in your life. It is with you every moment. It holds you softly to the earth. It keeps your feet on the ground, your body resting on the bed, and the blanket lying gently over you. Even when you are not thinking about it, gravity is there, steady and patient. And in space, gravity is there too. Space is not a place where gravity disappears. It is not a place where gravity stops working. Instead, space is a place where gravity becomes easier to notice in a different way. It guides moons around planets. It guides planets around stars. It gathers clouds of gas into glowing suns. It shapes galaxies, and it helps hold together great clusters of galaxies, spread across distances so large that the mind can rest instead of trying to measure them. So as we begin, you can imagine gravity not as something harsh or sudden, but as something quiet, a gentle connection between things that have mass, a steady tendency for objects to draw one another closer. The Earth draws you toward its center. You draw the Earth toward you as well, though the Earth is so massive that your pull on it is far too tiny to notice. This is one of the first peaceful ideas to keep in mind. Gravity is mutual. Everything with mass attracts everything else with mass. A stone attracts the Earth attracts the stone, the moon attracts the Earth attracts the moon, the sun attracts the planets, and the planets attract the sun. Every object is part of a web of quiet pulling. On Earth, we usually experience gravity as weight. When you stand, you feel the ground supporting you. Your body is being pulled downward, toward the center of the planet. The ground pushes back upward, and that is what you feel as your weight. When you lie down, the bed supports you instead. Gravity is still there, but your body can relax into support. In space, especially far from a planet's surface, gravity does not always feel like weight. That can be surprising. Astronauts orbiting Earth seem weightless. They float inside their spacecraft. Drops of water drift beside them. Their hair may lift softly around their heads. It looks as though gravity has vanished, but it has not vanished. The spacecraft, the astronauts, and everything inside are all falling toward Earth together. They are falling, but they are also moving sideways very quickly. Because they move sideways so fast, they keep missing the ground. They fall around the Earth instead of straight into it. This is called orbit. An orbit is a kind of continuous falling. It is a very gentle idea when you take it slowly. Imagine tossing a ball forward. It moves ahead, and gravity pulls it down. It lands on the ground. If you could toss it much faster, it would travel farther before landing. If you could toss it fast enough, and if there were no air to slow it down, the ground would curve away beneath it at the same rate that it fell. The ball would keep falling, but it would never reach the surface. It would circle the Earth. That is what a satellite does. That is what the moon does around Earth. That is what Earth does around the sun. The feeling of weightlessness in orbit comes because everything is falling together. The astronaut is falling. The spacecraft is falling. A pencil floating nearby is falling. Since all of them are falling at the same rate, nothing inside the spacecraft presses strongly against anything else. There is no floor pushing up against the astronaut in the usual way. So the astronaut feels weightless. Gravity is still strong there. In low Earth orbit, where many spacecraft travel, Earth's gravity is only a little weaker than it is at the surface. The astronauts are not beyond gravity. They are within it, completely, moving through it, held by it in a steady curve. This can be a soothing thought. Weightlessness is not the absence of gravity, it is the experience of falling freely. And free fall is a central idea in understanding gravity in space. If you were inside a quiet elevator, far away from any disturbance, and the elevator were falling freely, you would float inside it, not because gravity was gone, but because you and the elevator would share the same motion. There would be no pressure between your feet and the floor. You would not feel your weight. In a similar way, a spacecraft in orbit is like a falling room. It is always falling around the Earth. Now, let's step back a little and think about what gravity is, in a simple and restful way. For a long time, people understood gravity as a force between objects. Isaac Newton described it with great clarity. He explained that every object attracts every other object, and the strength of that attraction depends on two things. It depends on how much mass the objects have and how far apart they are. More mass means stronger gravity. More distance means weaker gravity. The Earth has a great deal of mass, so its gravity is strong near its surface. The Moon has less mass, so its surface gravity is weaker. On the Moon, you would weigh much less than you do on Earth, even though your body's mass would be the same. Your mass is the amount of matter in you. Your weight is how strongly gravity pulls on that mass. This distinction is useful and calm to remember. Mass stays with you. Weight depends on where you are. On Earth, you have one weight. On the Moon, a smaller weight. On Mars, something in between. Far from planets and stars, you can float in weightlessness. It is not that gravity disappears, but that everything is falling together. You might feel almost weightless, though tiny pulls from distant objects would still be present. Gravity weakens with distance, but it never truly becomes zero. It fades and fades, becoming very small, but it continues outward. The Earth pulls on the Moon. The Earth also pulls on the Sun, and on distant planets, and even on faraway stars, though very faintly. Every part of the universe is gently related to every other part through gravity. This does not mean everything rushes together at once. The universe is full of motion, distance, and balance. Objects may fall toward each other, circle each other, pass by each other, or join together over long spans of time. Gravity is steady, but the universe is spacious. Now we can move softly from Newton's view to another way of understanding gravity, given by Albert Einstein. Einstein described gravity not only as a force, but as a change in the shape of space-time. Space-time is a way of speaking about space and time together. Space tells us where things are. Time tells us when things happen. In everyday life, we often think of them separately. But in the deeper physics of the universe, space and time are connected. Mass and energy affect space-time. They curve it, and objects move along the curves. A common image is a stretched sheet with a heavy ball placed in the middle. The sheet bends around the ball. If a smaller ball rolls nearby, it may curve around the heavier ball, not because something invisible pulls it directly in the ordinary sense, but because the surface it moves on is curved. This image is not perfect, but it can help. The sun curves space-time around it. Earth follows a path through that curved space-time. We experience that path as orbiting the sun. Earth also curves space-time around itself. The moon follows that curve, orbiting Earth. You, resting on Earth, are also in that curved space-time. The ground stops you from following a free-fall path inward, so you feel weight. In Einstein's view, when you are standing on the ground, it is not that you are simply still while gravity pulls you down. Rather, the ground is pushing you away from the natural path you would follow through curved space-time. That push is what you feel as weight. When you are in orbit, falling freely, you are following a natural path. You feel weightless because nothing is preventing that motion. You and the spacecraft are simply moving along a shared path through space-time. This idea can feel abstract, but we do not need to hold it tightly. We can let it be simple. Matter tells space-time how to curve. Curved space-time tells matter how to move. And so, the planets move in calm, repeating paths. The moon circles Earth. Earth circles the sun. The solar system travels through the Milky Way. The Milky Way moves within a larger gathering of galaxies. All of it is shaped in part by gravity. Now let us return to orbit, because orbit is one of the clearest ways to see gravity working in space. An orbit happens when an object has the right combination of forward motion and inward falling. If an object has too little sideways speed, it falls down toward the larger body. If it has enough speed, it circles. If it has even more speed, it may follow a stretched orbit, moving close at one point and far away at another. If it has enough speed to escape, it may leave and not return. The speed needed to orbit depends on the mass of the object being orbited and the distance from it. Close to Earth, an object must move very quickly to stay in orbit. Farther away, it can move more slowly. The Moon, being far from Earth compared with a spacecraft in low orbit, travels around Earth more slowly than a nearby satellite, though its path is much larger. This is why many satellites circle Earth in different ways. Some are low and fast, completing an orbit in about an hour and a half. Others are much higher and slower. Some are placed so that they orbit Earth once every day, matching Earth's rotation. These are called geostationary satellites. From the ground, they seem to hang over one region of the planet. They are not hanging still. They are falling around Earth in just the right rhythm. Again and again, gravity and motion create balance. The Moon is also held in this balance. It is falling toward Earth and moving sideways. It keeps missing Earth, and so it remains in orbit. At the same time, the Moon's gravity pulls on Earth. This pull helps create tides in the oceans. The water on the side of Earth facing the Moon is drawn slightly toward it. Water on the far side also forms a bulge, because Earth itself is pulled a little more strongly than the water on the far side. As Earth rotates, coastlines pass through these bulges, and the sea rises and falls. The sun also affects tides, though the Moon has the stronger influence on Earth's oceans because it is much closer. When the sun, Earth, and Moon line up, tides can be higher. When they are at right angles, tides can be more moderate. Even here in the quiet rise and fall of the sea, gravity in space is present. The ocean responds to the Moon and to the sun. The water moves in a slow rhythm, connected to bodies far beyond the shore. Gravity also explains why planets are round. When an object in space becomes massive enough, its own gravity pulls material inward from all directions. Over time, this inward pull smooths the object into a rounded shape. Small asteroids can be irregular, like stones, because their gravity is weak, and their material can hold unusual shapes. But larger bodies, such as planets and moons, become nearly spherical. They are not always perfect spheres. Rotation can make them bulge slightly at the equator. Earth is a little wider around the middle than from pole to pole. But gravity still gives planets their overall roundness, pulling matter toward the center. Gravity also helps build stars. In space, there are vast clouds of gas and dust. These clouds may be cold and spread out. Over time, small regions can become slightly denser. Gravity pulls more material into those denser regions. As more gas gathers, the pull becomes stronger. The cloud contracts. The center grows hotter and denser. Eventually, if enough mass gathers, nuclear fusion begins, and a star is born. Fusion is the process that powers stars, including our sun. In the core of the sun, hydrogen atoms combine to form helium, releasing energy. But gravity is what gathers the gas and presses it together strongly enough for fusion to begin. So, in a quiet way, Gravity helps light the stars. Once a star exists, gravity continues to shape its life. Gravity pulls inward. Pressure from heat and radiation pushes outward. For much of the star's life, these forces balance. The star remains stable, shining steadily over millions or billions of years. Our sun is in such a balance now. Its gravity pulls its material inward. The energy produced in its core pushes outward. The result is a steady star, warm and bright, giving energy to the planets around it. Planets form in disks of gas and dust around young stars. Tiny grains collide and stick together. Larger clumps form. Gravity helps these clumps gather more material. Over time, planets emerge. Some become rocky worlds. Some gather thick envelopes of gas and become giant planets. The solar system, in this sense, is a memory of gravity at work. The sun at the center, the planets in their paths, moons around planets, asteroids, comets, dust, and ice, all moving under the influence of gravity. Each planet follows an orbit that is not a perfect circle, but an ellipse, a gently stretched circle. This was described by Johannes Kepler, who studied planetary motion carefully. A planet moves a little faster when it is closer to the sun, and a little slower when it is farther away. This is another quiet pattern of gravity. When Earth is slightly closer to the sun, it moves slightly faster. When it is slightly farther away, it moves slightly slower. But the change is gentle. The year continues. The seasons come from Earth's tilted axis, not mainly from distance to the sun. Gravity keeps the orbit steady, while the tilt gives us the familiar rhythm of seasons. Now let us consider what happens when gravity is very strong. A massive planet has stronger gravity than a smaller one. A star has stronger gravity still. And when a great deal of mass is packed into a very small region, gravity can become extremely intense. This can produce a black hole. A black hole is a region where gravity is so strong that within a boundary called the event horizon, not even light can escape. It is not a cosmic vacuum cleaner, pulling in everything from unlimited distances. From far away, a black hole's gravity can behave much like the gravity of any object with the same mass. If the sun could somehow be replaced by a black hole with the same mass, Earth would continue orbiting at the same distance. It would become dark and cold, but it would not be suddenly pulled inward, simply because the sun had become a black hole. A black hole becomes unusual because its mass is compressed into such a small space. Near it, space-time is curved very strongly. Time and space behave in ways that differ greatly from everyday experience. But even black holes follow the same broad idea. Mass curves space-time. Objects follow paths through that curvature. Gravity, even in its strongest forms, is part of the same universe of motion and relation. Most of the time, in our calm tour of space, gravity is not something to fear. It is the reason structures exist. Without gravity, matter would not gather into stars. Planets would not form. Moons would not orbit. Galaxies would not hold their shapes. The universe would be much more diffuse, much less organized. Gravity is the great gatherer. It gathers softly over time. It gathers dust into worlds, gas into stars, stars into galaxies, galaxies into clusters. And it does this across timescales that are often far beyond human life. Gravity is patient. A cloud of gas may take millions of years to collapse into a star. Galaxies may take billions of years to form and merge. The moon has circled Earth for billions of years. Earth has circled the sun again and again, year after year, in a long and steady rhythm. Now let us think about galaxies. A galaxy is a vast collection of stars, gas, dust, and dark matter, all held together by gravity. Our galaxy, the Milky Way, contains hundreds of billions of stars. The sun is one star among them. It orbits the center of the Milky Way, taking around 200 million years to complete one circuit. The stars in a galaxy are not fixed in place. They move. They orbit the galactic center. Their motions are guided by the combined gravity of all the matter in the galaxy, including matter we can see and matter we cannot see directly. This unseen matter is called dark matter. Scientists infer its presence because galaxies rotate in ways that cannot be explained by visible matter alone. Stars far from the centers of galaxies move faster than expected if only visible stars and gas were providing gravity. Something else appears to contribute additional gravitational pull. Dark matter does not seem to emit light, absorb light, or reflect light in ordinary ways, but it has gravity. And because gravity shapes motion, scientists can study dark matter by watching how galaxies move, how light bends, and how large structures form. This brings us to another gentle effect of gravity in space: the bending of light. In Einstein's theory, gravity curves spacetime, and light follows the curves of spacetime. So light passing near a massive object can bend. This is called gravitational lensing. A galaxy or cluster of galaxies can act like a lens, bending and magnifying the light from more distant objects behind it. Sometimes this creates arcs, rings, or multiple images of the same distant galaxy. It is one of the ways astronomers study both visible matter and dark matter. Even light, which has no rest mass, is affected by gravity because it travels through curved spacetime. This is a soft but remarkable idea. Gravity does not only guide planets and moons. It also shapes the paths of beams of light traveling across the universe. When we look deep into space, we are also looking back in time. Light takes time to travel. Moonlight takes a little more than a second to reach Earth. Sunlight takes about 8 minutes. Light from the nearest stars takes years. Light from distant galaxies can take millions or billions of years. Gravity has been acting during all that time. It has shaped the objects that emitted the light. It has shaped the path the light followed. It has influenced the universe from its earliest periods to the present moment. Now we can return again to the experience of weightlessness, because it is one of the most common images people have of gravity in space. Astronauts floating in orbit are often described as being in zero gravity. In everyday language, that is understandable. But scientifically, it is more accurate to say they are in microgravity. The gravity there is not zero. The feeling of weight is greatly reduced because they are in free fall. Inside the spacecraft, a person can push gently off a wall and glide across the cabin. Small objects float beside them. Liquids form rounded shapes because surface tension becomes more noticeable when weight is not pulling them downward into a container. The body also changes in microgravity. Fluids shift. Muscles and bones no longer work against weight in the same way. So astronauts exercise to help maintain strength. All of this happens not because gravity has disappeared, but because the spacecraft and everything inside share the same falling motion. If a spacecraft were far from any planet, moon, or star, gravity would be much weaker, but not entirely gone. Distant objects would still exert tiny pulls. In practice, the spacecraft might drift according to the combined gravitational influence of many bodies. Space travel is often a matter of understanding these pulls and using them carefully. Mission planners use gravity to guide spacecraft. A spacecraft can pass near a planet and receive a change in speed and direction. This is called a gravity assist. The spacecraft falls toward the planet, swings around it, and leaves on a new path. The planet's motion around the sun contributes a small amount of energy to the spacecraft's journey. Gravity assists have helped spacecraft travel to the outer planets and beyond. They are examples of moving with gravity rather than against it. A quiet exchange of motion, arranged with great care. Gravity is also why escape velocity matters. To leave a planet and not fall back, this required speed is called escape velocity. From Earth's surface, it is about 11.2 kilometers per second. if there were no air resistance and no additional propulsion. Rockets do not usually reach this speed all at once from the ground. They accelerate over time, climbing and gaining speed, using engines to shape their path into orbit or beyond. To enter orbit, a spacecraft does not simply go upward. It must also gain sideways speed. Going up helps it reach thinner air and a suitable altitude. Going sideways fast enough allows it to fall around Earth. This is why rocket launches curve as they rise. They are not only climbing away from Earth, they are building the speed needed to orbit. Once in orbit, a spacecraft can remain there with little fuel, except for adjustments. In low orbits, a very thin atmosphere still causes drag, slowly reducing altitude. In higher orbits, objects can remain for very long periods. The balance of orbit can be disturbed, but it can also be very stable. The Moon's orbit, for example, changes slowly over time. The Moon is gradually moving away from Earth by a few centimeters each year. This happens because of tidal interactions between Earth and the Moon. Earth's rotation and the Moon's orbit exchange energy and angular momentum. The effect is tiny from year to year, but over long times it matters. Gravity often works like this. Small effects, repeated patiently, become meaningful across long spans of time. Tides slow Earth's rotation very gradually. The Moon recedes slowly. Orbits shift. Stars move. Galaxies change. The universe is not still, but much of its motion is slow and graceful. Now let's think about Lagrange points, another quiet feature of gravity in space. When two large bodies orbit each other, such as the Sun and Earth, there are certain places where the gravitational pulls and orbital motion balance in useful ways. These places are called Lagrange points. A spacecraft near one of these points can stay in a relatively stable position with less fuel than might otherwise be needed. Some space telescopes are placed near Lagrange points. From there, they can observe the universe with a steady view. These points are not magical still places, but regions where the combined gravity of two bodies creates a helpful balance for orbiting objects. Again, gravity is not just pulling inward, it is part of a pattern. Motion, distance, mass, and curvature all work together. If we imagine the solar system from far above, we might see the planets moving in broad, nearly flat paths around the Sun. The inner planets move more quickly. Mercury, close to the Sun, completes its orbit in only 88 Earth days. Venus takes longer. Earth takes 1 year. Mars takes nearly 2 Earth years. Farther out, Jupiter takes almost 12 years, and Neptune takes about 165 years. The farther a planet is from the Sun, the longer its path, and the weaker the Sun's gravity at that distance. So the planet moves more slowly and takes longer to complete an orbit. This pattern is a peaceful one. Close objects orbit quickly. Distant objects orbit slowly. Gravity fades with distance, and motion adjusts. Moons follow similar patterns around their planets. Some moons are close and fast. Others are far and slow. Rings around planets such as Saturn's rings are made of countless small icy and rocky particles, each one orbiting Saturn according to gravity. The rings look like smooth bands from far away, but they are made of many individual pieces, all following their own paths. Gravity also creates gaps and waves in rings. Moons can tug on ring particles, clearing spaces or shaping edges. Even small moons can have noticeable effects, because their pulls repeat again and again. Repeating gravitational pulls are called resonances, when orbital periods form simple ratios. For example, one object might orbit twice for every one orbit of another. These patterns can stabilize some orbits and disturb others. Resonance helps explain gaps in asteroid belts, patterns in planetary rings, and the motions of some moons. The universe contains many such rhythms. Some are simple, some are complex. but all are shaped by the steady influence of gravity. Now we can speak gently about falling. Falling is often thought of as moving downward, but in space, falling can mean following gravity's path. A comet falling toward the sun may speed up as it approaches, then slow down as it travels away. It may return again after many years, or it may leave the solar system if its path is open. A planet is falling around a star. A moon is falling around a planet. A spacecraft in orbit is falling around Earth. Falling in this sense is not necessarily a brief event. It can be a long, stable motion. This is why gravity can create both closeness and distance. It pulls objects inward, but if they have sideways motion, it can keep them circling instead of colliding. Orbit is a falling that does not end, and this is one of the central answers to how gravity works in space. It works by drawing masses together, by curving paths, by shaping motion. But because objects are already moving, gravity often bends their paths rather than simply making them fall straight together. The Earth does not fly away from the sun because gravity bends its path inward. The Earth does not fall into the sun because it has sideways motion. The result is orbit, a calm balance, not stillness, but steady motion. Now, as we continue, let us consider how gravity changes with distance in a little more detail. Newton's law of gravity says that the pull between two objects becomes weaker with the square of the distance between them. If the distance doubles, the gravitational pull becomes 1/4 as strong. If the distance triples, it becomes 1/9 as strong. Light also spreads out in a similar way. Sound and other effects can spread out too, depending on the situation. The idea is that as influence spreads through space, it is shared over a larger and larger area. So, near Earth, gravity is strong. Farther away, it weakens. But because Earth is massive, its influence extends far enough to hold the moon, and to affect satellites, and to contribute to the motion of objects in the solar system. The Sun, much more massive than Earth, dominates the gravity of the solar system. It contains more than 99% of the solar system's mass. That is why planets orbit the Sun. But planets still influence each other. Jupiter, the largest planet, tugs on asteroids, comets, and other planets. Its gravity helps shape the asteroid belt and can redirect smaller bodies. Every object contributes, according to its mass and distance. No object is completely alone. This is true even at the scale of the universe. Galaxies gather into groups. Groups gather into clusters. Clusters are connected by vast filaments of matter, forming a cosmic web. Gravity helps create this structure, drawing matter into denser regions over billions of years. At the same time, the universe itself is expanding. On the largest scales, distant galaxies move away from one another as space expands. Gravity works within this expansion, slowing it in some places, binding galaxies together in others. Our own Milky Way and the Andromeda Galaxy are moving toward each other because their mutual gravity overcomes the general expansion between them. In several billion years, they are expected to merge into a larger galaxy. This sounds immense, but the stars inside galaxies are so far apart that direct collisions between stars are unlikely. The galaxies will pass through and reshape each other gravitationally, and over time, settle into a new form. Gravity reshapes without needing contact. That is another quiet idea. Gravity acts at a distance. The moon does not touch the ocean, yet tides rise. The sun does not touch Earth, yet Earth orbits. A galaxy bends the light of another galaxy far behind it. Gravity connects across emptiness. Although space seems empty, it is filled with these relationships. Now we may gently ask, why do all objects fall at the same rate in a gravitational field if air resistance is removed? On Earth, a feather falls slowly because air pushes against it. A stone falls quickly because air affects it less. But in a vacuum, without air, they fall together. This was shown on the moon, when a hammer and a feather were dropped at the same time and reached the ground together. Gravity accelerates objects in the same way, regardless of their mass, if other forces are not interfering. A heavier object feels a stronger gravitational pull, but it also has more inertia, meaning it resists changes in motion more. These two effects balance, so the acceleration is the same. This is part of what makes freefall feel weightless. All parts of you and the spacecraft around you accelerate together under gravity. Einstein took this very seriously. The equivalence between gravity and acceleration became a foundation of general relativity. In a closed room, if you felt the floor pushing against your feet, you might not know whether you were standing on a planet or accelerating through space. If you floated freely, you might not know whether you were far from gravity or simply falling with everything around you. The feeling can be the same. This connection between gravity and acceleration is one of the deep clues that led to the idea of curved spacetime. But for tonight, we can let the deeper mathematics rest. We can keep the simple picture. Gravity guides motion. Free fall removes the feeling of weight. Orbits are falling paths around larger bodies. Now, let us imagine a quiet spacecraft traveling from Earth to the moon. At first, it launches from Earth, rising through the atmosphere, pushed by rocket engines. It gains altitude and sideways speed. It enters orbit around Earth. Then, with another carefully timed burn, it stretches its orbit so that its path reaches toward the moon. As it travels, Earth's gravity continues pulling it. The moon's gravity becomes stronger as it gets closer. There is a region where Earth's pull and the moon's pull are comparable, though the full motion is more complex because everything is moving. The spacecraft does not travel in a straight line. It follows a curved path shaped by gravity and by its own speed. Near the moon, the spacecraft can fire its engine to slow down and enter lunar orbit. Without slowing, it might swing around the moon and return toward Earth, or continue on another path. With the right change in speed, it becomes captured by the moon's gravity. This word, captured, in orbital mechanics, simply means that the object's path becomes bound to another body. It remains in orbit, unless changed by another force. A moon can capture dust. A planet can capture a spacecraft. A star can hold planets in bound orbits. Gravity defines these relationships. But orbit is not a rigid track. There are no rails in space. An orbit is a path that results from motion under gravity. Change the speed, and the orbit changes. Speed up at the right point, and the orbit can grow larger. Slow down, and it can shrink. A small push at one place can have a large effect later, because space motion unfolds over time. This is why space navigation is careful and patient. It uses timing, geometry, and gravity together. The same principles apply naturally to comets and asteroids. Some asteroids orbit the Sun in the asteroid belt between Mars and Jupiter. Others cross Earth's orbit. Some are nudged by the gravity of planets. Over long times, small changes can shift their paths. Astronomers study these orbits carefully, using gravity to predict future positions. Prediction is one of the great successes of gravitational science. The motions of planets, moons, and spacecraft can be calculated with remarkable precision. Not perfectly forever, because many body systems can become complex, but often with enough accuracy to send spacecraft across millions or billions of kilometers. Gravity, though invisible, leaves clear traces in motion. If you know how something moves, you can learn about the gravity around it. This is how Neptune was discovered. Uranus was not moving exactly as expected. Astronomers reasoned that another planet might be tugging on it. They calculated where that planet should be, and Neptune was found. Its presence was revealed by gravity before it was seen clearly as a planet. In the same way, unseen exoplanets, planets around other stars, can be discovered by the tiny gravitational wobble they cause in their stars. A planet orbits a star, but the star also moves slightly in response. Both orbit their shared center of mass, called the barycenter. For the Sun and Earth, the barycenter is very close to the Sun's center, because the Sun is so massive. For the Sun and Jupiter, the barycenter can lie just outside the Sun's surface, because Jupiter is much more massive than Earth. The idea is simple. Two bodies do not have one completely still center and one moving object. They both move around a common balance point. This, too, is gravity being mutual. The Earth pulls on the Sun. The Sun pulls on Earth. The Sun's motion is tiny compared with Earth's orbit, but it is real. In binary star systems, two stars can orbit a shared barycenter. Some are close, circling each other in days or hours. Others are far apart, taking years or centuries. Gravity binds them together. In systems with 3 or more stars, motion can become more complicated. Some arrangements are stable, with 2 stars close together and a third farther away. Others may shift over time. Gravity can create graceful order, and it can also create complexity. But tonight, we stay with the gentle pattern: mass, distance, motion, orbit. Now let us consider gravity on different worlds. On the Moon, gravity is about 1/6 of Earth's. A person could jump higher and fall more slowly. Dust kicked up by a step would follow a clean arc, because there is almost no atmosphere to swirl it around. The Moon's gravity is strong enough to hold the Moon together and keep objects on its surface, but not strong enough to hold a thick atmosphere over billions of years. Mars has about 38% of Earth's surface gravity. You would weigh less there, and movement would feel different. Mars can hold a thin atmosphere, but not one as dense as Earth's. Its lower gravity, along with other factors, has allowed much of its atmosphere to be lost over time. Jupiter has much stronger gravity, though there is no solid surface like Earth's to stand on in the familiar way. Its mass shapes a large family of moons. Some of these moons are worlds of great interest, such as Europa, with an icy surface and likely ocean beneath, and Ganymede, the largest moon in the solar system. Gravity can also heat moons. When a moon follows an orbit that is slightly stretched, it may be flexed by the changing pull of its planet. This flexing creates internal heat. Jupiter's moon Io is strongly affected this way, making it volcanically active. Europa may also be warmed, in part by tidal flexing, helping maintain its subsurface ocean. So gravity does more than move worlds. It can warm them, stretch them, shape their interiors, and influence their environments. Earth itself is shaped by gravity in many layers. Gravity holds the atmosphere close. It gives rivers a direction downhill. It helps create pressure deep within the planet. It keeps the moon near us. It holds the planet in orbit around the sun. And still, gravity is the weakest of the 4 fundamental forces in physics when compared at small scales. Electromagnetism, the strong nuclear force, and the weak nuclear force all have important roles. A small magnet can lift a paperclip against the gravity of the entire Earth. That shows how weak gravity can be, compared with electromagnetism. But gravity has 2 special qualities. It always attracts, as far as we know in ordinary matter, and it acts over very long distances. Positive and negative electric charges can cancel each other, but mass does not cancel in the same way. So over large cosmic distances, gravity becomes the force that shapes stars, planets, and galaxies. It is weak up close compared with other forces, but vast in its reach. Now slowly we can bring together the main ideas. Gravity works in space because mass and energy influence the motion of other mass and energy. In Newton's description, objects attract each other with a force that grows stronger with mass and weaker with distance. In Einstein's description, mass and energy curve spacetime, and objects follow paths through that curved spacetime. In everyday terms, gravity is what makes things fall. In space, it is what makes things orbit. It is what holds moons near planets, planets near stars, and stars within galaxies. Weightlessness does not mean gravity is absent. It usually means free fall. Astronauts in orbit float because they and their spacecraft are falling around Earth together. Orbits are not places where gravity has stopped. Orbits are possible because gravity is present. This is a gentle correction to a common misunderstanding. Space is not gravity-free. Space is full of gravity, though its strength changes from place to place. Near planets and stars, it can be strong. Far away, it can be weak. But it extends outward, connecting objects across great distances. Gravity builds, holds, bends, and guides. It builds stars from clouds. It holds planets in their paths. It bends light around galaxies.
It guides spacecraft through carefully planned journeys. It shapes the universe quietly, over time.
And now, as we move toward the end, we can let the ideas become simpler and softer. Imagine Earth turning slowly beneath the moon. The oceans rise and fall. The moon continues along its orbit, falling around Earth. Earth continues along its orbit, falling around the sun. The sun moves within the Milky Way. The Milky Way moves among other galaxies. Nothing needs to be hurried. Gravity does not hurry. It acts continuously, steadily, patiently. A satellite circles Earth again and again. A planet returns to the same part of its orbit year after year. A moon keeps time with its planet. A galaxy turns slowly, carrying its stars around a hidden center of mass. Everywhere, motion and gravity are together. If you picture an astronaut floating in a spacecraft, you can remember that they are not outside gravity. They are sharing a fall with the spacecraft. They are in a quiet curve around Earth. The planet is below them, pulling them inward, while their sideways motion carries them around and around. If you picture the moon, you can remember that it is not simply hanging in the sky. It is moving, falling, circling, held by gravity and motion together. If you picture the sun, you can remember that its gravity holds the planets, while deep inside it, gravity also helps maintain the pressure that allows it to shine. If you picture the stars of the Milky Way, you can remember that each one moves in the galaxy's combined gravitational field, part of a slow and immense pattern. Gravity is invisible, but not hidden. It can be seen in curves, in orbits, in tides, in round planets, in the paths of comets, in the bending of light, in the gathering of galaxies. It is present in the quiet order of space, and it is present here too, in the gentle feeling of rest. The same gravity that holds the moon in orbit also holds you softly against the Earth. The same Earth that circles the sun supports you now. The same universe that moves in wide, patient curves is around you, steady and calm. There is no need to follow every detail now. The main idea is enough. Gravity is the gentle attraction between masses. Gravity is the curve of spacetime. Gravity is why falling can become orbit. Gravity is why space has structure. Gravity is why worlds stay near stars, and moons stay near worlds. It is steady, it is quiet, it reaches far. And as this thought settles, you can let the universe be spacious again. Planets continue in their paths, moons continue around them, stars continue to shine, galaxies continue their slow turning. Gravity keeps working, without effort, without sound, without needing attention. It has worked for billions of years. It will continue while you rest. Earth turns slowly. The moon drifts onward. The sun holds the planets in their familiar paths. Far away, stars move through the galaxy, and galaxies move through the wider dark. All of it is connected by gravity. All of it is moving gently. All of it can continue without being held in the mind. And so, the question, how gravity works in space, can become very simple now. It pulls, it curves, It guides. It lets things fall together or fall around each other. It shapes the quiet motions of the universe. And here, near the surface of Earth, it offers a steady downward softness, a sense of being held, a sense of being supported, a sense that the planet is beneath you, calm and constant. The night can continue. The planets can continue. The moon can continue. Gravity can continue. And you can rest while the universe moves slowly on.